Good morning again. Thanks for everyone on the webinar this morning for joining us. I'm Megan Hoy, the Engagement Manager at the Center for Energy and Environment, and we're really excited to have you here with us to for some very intriguing and alluring technical learning. Without further ado, I would like to introduce Mary Sue Lobenstein, who is the Conservation Improvement Program Research and Development Program Administrator at the Department of Commerce, Division of Energy Resources, to kick us off with an introduction for today's webinar.
Welcome to the Conservation Applied Research and Development CARD webinar. As Megan said, I'm Mary Sue Lobenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. And this webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund. The Applied Research and Development Fund was established in the Next Generation Energy Act of 2007. Its purpose is to help Minnesota utilities achieve their 1.5% energy savings goal by identifying new technologies and strategies to maximize energy savings, improving the effectiveness of energy conservation programs, and documenting CO2 reductions from energy conservation programs. $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Since the legislation was enacted, the CARD program has had 8 funding cycles with 21 RFPs posted, and actually we now have 22 RFPs since we just posted our latest RFP this past Monday. It also has received nearly 380 proposals, and we funded 92 research projects representing over $21 million in research funds. As you can see by the pie chart, projects funded to date have been in all building sectors. The subject of today's webinar is a project which investigated the duct leakage in large commercial and institutional buildings. It'll be presented by the Center for Energy and Environment.
Thank you, Mary Sue. As a nonprofit whose mission is to increase energy efficiency while strengthening the economy and improving the environment, on the ground, the Center for Energy and Environment works to discover and deploy the most cost-effective solutions for a healthy and low-carbon economy. We are very excited to have with us today Josh Quinnell, who's a senior research engineer at the Center for Energy and Environment, to present on the cost-effectiveness of duct retrofit and leakage reduction. Just a little bit of housekeeping before we go any further. We're definitely going to be saving some time at the end of the webinar to go through questions that you might have as you listen, but to help keep your questions live and the brain turning. If you have questions as we're moving through the presentation, feel free to enter those at any time in the question dialog box on the right side of your screen in the navigation bar. We may even, if those questions are relevant to topics we're still discussing, we may even try to interject those throughout. Also, we are recording this webinar, and we will be posting the recording as well as the slides within a few days of it being completed. And so you can look for that on our webinar, and we'll be sending out that link to all those attending. So we're very excited to have Josh with us today. Dr. Josh Quinnell, though he's too humble to say that himself, so I get to say it, is a senior research engineer at CEE, and Josh has had 8 years of research experience in solar energy, heat and mass transfer, and renewable technology development. Currently, Josh is working on building energy efficiency projects, including commercial and institutional HVAC, duct leakage, condenser boiler, efficiency monitoring, optimization of energy recovery ventilation or ERV systems, and residential garage contaminant transport. Josh is also investigating prospects for showcasing solar energy and renewable energy storage in Minnesota. Prior to CEE, Josh spent time in ZAE Bern, which is in Munich, Germany, researching thermochemical energy storage cycles for solar and district energy applications. Josh obtained his master's degree in 2008 and his PhD in 2012 in mechanical engineering from the University of Minnesota. All right. With that, I will turn it over to Josh to help us dive in.
All right, terrific. Thank you, Megan, and thank you, Mary Sue. So today I'm going to talk about a project that we have been working on for several years now that is wrapped up, well, depending on how you define it, sometime in the last year. As Mary Sue said, this is a card research project, and in this project we covered a lot of ground. We essentially started from scratch when we were trying to understand whether retrofit duct sealing can be a savings measure. And what that meant was we first needed to characterize what kinds of duct systems are found in commercial institutional buildings in Minnesota. And from that we moved on to quantifying duct leakage. We measured duct leakage and tried to estimate its energy impacts. Following that, we decided to try out retrofit duct sealing. We tried a bunch of different styles and techniques for sealing ducts and quantified the leakage reduction and the energy savings. After that, we continued to move forward when we tried to find whether we could identify ways to find the most cost-effective duct sealing opportunities. And then lastly, we kind of completed this project over the past year by testing what we found in a short pilot program to see whether retrofit duct sealing is a cost-effective savings measure. And from all that, we've compiled a final report that is now in the process of, I think, being made available. I think you'll find an executive summary on our website right now. But today's talk, I'm going to focus on just a few aspects of this work. Hopefully to convince you that duct leakage is an opportunity, retrofit duct sealing does work, and we can identify cost-effective opportunities. So I'll start first by jumping into some background so we all get on board with what we mean when we talk about duct leakage. So duct leakage is any unintended flow into or out of an air distribution system, or the ductwork. The vast majority of air distribution systems in C&I buildings are sheet metal ducts that are constructed on site. These ducts are not airtight. Duct leakage occurs throughout the duct system. This includes longitudinal seams, transverse joints, branch takeoffs, wall penetrations, damper shafts, fasteners, etc., etc. I can go on forever to talk about all the possible leakage paths. It generally does not include accessory leakage or equipment leakage, for example, air handlers and VAV boxes. Although, as an aside, it is often difficult to distinguish leakage from those components from duct leakage during regular testing. That said, there's some basic requirements for duct leakage. It requires both an airflow and a pressure drop. Importantly, if you have a duct system that moves 1,000 CFM, you obviously have an upper limit for how much duct leakage there could be. The other side of that is the pressure drop. There's a difference of pressure inside a duct and outside a duct, and that is the driving force for the duct leakage. So the higher the pressure, the higher the leakage. We talk about duct leakage, at least in the literature, in several different ways. Two of the most common are the leakage fraction and estimated leakage area. The leakage fraction is essentially just the fraction of air of the total flow rate that doesn't make it to the outlet of the system. So if you have, again, our 1,000 CFM system with 10% leakage, we're leaking 100 CFM out of that system before it reaches the final termination. Estimated leakage area tries to estimate the total area of the leaks in the system. So this is gives you an impression of how big maybe one giant hole would be to have to leak that much air. So again, returning to our 1,000 CFM example, we might have leaks that add up to about 10 square inches to leak our 10% of air, or 100 CFM. In this project, and mostly in our final report, we really like talking about the leakage fraction. At the end of the day, what matters in an individual system is, at its nominal operating conditions, how much air does it leak. That's the air that's not available for ventilation, heating, cooling, and that's the air that's associated with energy penalties. So despite what I just said about all the many ways that air can leak out of duct systems, often people, and myself included, still imagine duct leakage to look like this. This is a branch takeoff that was not completed. Evidently, the contractors decided to supply air through some other branch duct, and their solution here was to cap this branch with a balancing damper. You can see that the balancing damper doesn't do that good of a job sealing the duct, and we get a lot of leakage around the perimeter. That said, although these things do occur, they're not very common. This is generally not what duct leakage looks like in practice. In practice, this is what duct leakage looks like. And I hope to convey here that it's very hard to see. This is a supply plenum that actually looks nice. The workers were very diligent. You can see there's all sorts of notes all over the inside of the ductwork that they recorded as they were putting it together. In fact, I even had to redact the name of the building because they probably did some off-site fabrication. But what we can see here is that just in this short, small supply plenum, we have tens, if not hundreds of feet of seams and joints. And it's all these seams and joints between the different components of the duct system that add up to give us the duct leakage we measure and the duct leakage that causes energy penalties. So I'll pause here briefly to say that there's a lot more in our report about kind of the state of sealing with respect to codes and with respect to the attitudes on duct sealing and duct leakage from field personnel, including code officials, sheet metal workers, tab contractors, etc., and design engineers. Here I just kind of want to set the ground briefly so that we have a starting point to talk about duct leakage. So historically and still commonly today, duct leakage is not considered an energy efficiency issue. It's mainly a performance issue. Consequently, when a duct system gets built, if it has a lot of duct leakage, that's generally overcome with more fan power. Over the last 20 years, codes on duct sealing have changed in little ways, but they generally haven't resulted in much. I can say that the recent code revision in 2015 was probably the most significant change, and that updated code to require sealing on low pressure ductwork, and low pressure ductwork is generally below 2 inches. High pressure, medium and high pressure ductwork is above 2 inches and above 3 inches, and that ductwork has always required significant amounts of sealing as well as testing to make sure that leakage is not too severe. Nonetheless, there's been this kind of growing body of literature that suggests that duct leakage, even at low pressures, can have very real energy penalties, and there are savings opportunities. Most of this work came out of California over the last 10 or 20 years. Researchers there initially started measuring duct leakage in relatively low pressure systems. For example, Ray in 2005 showed that measured leakage in 10 systems averaged about 15%. 70% of the systems had leakage of 9% or greater, and they only found 3 systems that they called tight. The same group also did some energy modeling and in some cases measurements to show that if you do seal this leakage, you end up with significant fan energy savings on the order of 20 to 50% when you reduce that leakage. And kind of one of the climax of that work out in California is that they developed a new process for sealing ductworks based on an aerosol system. And they showed very early on that it was highly effective for reducing duct leakage. They demonstrated 70 to 90% reductions in duct leakage on early tests. So let's dig into this a little bit more. So the main issue is that duct leakage increases fan energy. Here I've got this cartoon, which is some arbitrary supply fan in an air handler, and it's delivering air through a ductwork here into the space. I mentioned we have this accumulation of all these leaks. Air that leaks out of this duct system before it reaches the final diffusers obviously doesn't do its intended thing, which is to supply ventilation, heating, and cooling to the space. Thus, the fan energy that we use to move that air is completely wasted. And remember, this is the accumulation of small leaks. It's seams that run the entire length, it's joints you find every 8 or 10 feet, and it's the connections, penetrations, and access panels you find throughout the system. And even these small leaks have big energy penalties. If you are aware of the kind of the affinity laws, you know that power scales with flow rate cubed. So even small changes in flow rate or duct leakage result in significant increases in fan power. So for supply systems, this tends to be a exponent of about 2.4, and exhaust systems exponent of 3. But just to give you an example, if you have 10% duct leakage, you're going to see roughly 15 to 20% increase in fan power. And that's at kind of a moderate amount of duct leakage. Once you get into high rates of duct leakage, like 20 to 25%, you see upwards of 50% increase in fan power. I mean, these are major, major inefficiencies. If you can imagine in a building with a lot of air handlers, if you aggregate duct leakage over a lot of these big blowers, we're talking about tens, if not hundreds of kilowatts of wasted fan energy. It doesn't really end there. In some systems, we have significant thermal penalties also associated with duct leakage. So I've got this cartoon here of a mixed air handler unit. We borrow our supply fan from before. This time it has supply ducts, and those supply ducts are traversing a ceiling plenum. So above a drop ceiling, the supply ducts run out to the diffusers. And that ceiling plenum actually serves as the return pathway for the return air. In this situation, our supply air is leaking directly into our return duct, the ceiling plenum. If we follow that supply leak from our supply duct through our leakage path right into our return, it finds its way directly back into the return side of the system. The air has not provided ventilation. It hasn't provided heat or cooling. It's short-circuited the building effectively. And then it passes through the return fan. Lost my little cursor here. There you go. And at some point, we exhaust a fraction of that air that we conditioned, we moved out the building without it doing anything for us. And the thermal energy we used to condition that air is now lost to us. This fraction of air depends on how much, this fraction of thermal energy loss depends on how much outside air we're pulling in the system. In most systems, this might be 20 or 30%. In exhaust systems or 100% outside air systems, this is a high fraction, 100%. So we got kind of hit twice in some systems. We have thermal energy penalties and fan energy penalties. It turns out the thermal energy penalties are a little bit more building and system specific. Like I said, they depend heavily on outside air. They also depend on building pressure. But we do see significant losses. For example, a regular supply system in a ceiling return plenum might have typical outside air fractions somewhere between 20 and 40%. At 10% duct leakage, we're seeing somewhere around 2 to 8% of lost thermal energy. So 2 to 8% of the energy put into your flow from a heating coil is essentially being evacuated out the building without doing anything for us. In Minnesota, that's a really big deal. We have a very high heating load. The situation is even more extreme in 100% outside air systems and or exhaust systems, where we essentially have a nearly 1-to-1 ratio of leaked CFM with lost thermal energy. So I hope that I've started to convince you that in some cases at least, that there is an opportunity for energy savings from leaky ducts. In other words, leaky ducts can cause significant energy penalties. The next step here is to share our experiences in what duct leakage looks like in Minnesota commercial and institutional buildings. And to do this, we did a lot of measurements. Part of this program was to actually investigate measurement techniques for trying to quickly estimate duct leakage in systems. We spent a lot of time learning how to make good measurements, and at the end of the day, we ultimately settled on the tried and true static pressure test. This method is very accurate when done right, and it's fairly simple to do right. Most important thing is that when we do this test, we measure duct leakage at a representative operating pressure. So this often requires us to measure the pressure beforehand. And it's even better to take what we call a multi-point test, where we test the pressure over, test the duct leakage over multiple pressures. This lets us produce what we call a characteristic curve for that duct section, and that really enables us to understand how it will leak over a variety of pressures, pre and post sealing. So a static pressure test, it's pretty simple. I'll go through that really quick. We basically shut off an air handler and isolate a piece of ductwork. This is a cartoon here of a schematic of maybe a downstream branch of a VAV box. We block the upstream portion of this section at the VAV like reheat coil. We put in some duct pressure measurements in that system. We block the outlets. In this case, it's the diffusers. And then we take a calibrated fan and we connect it to this duct system. We then blow air in this duct system. Since we've blocked it all off, air can only escape out the leaks, and we simply record what the flow rate is on our fan at the pressure of the ducts. That gives us a very good estimate of what the duct leakage is at that operating pressure. So we applied this static pressure testing and some other types of measurements in a lot of different buildings. We started initially from a list of 63 systems. We ruled out a lot of them for various reasons, and we ended up spending significant time on about 30 systems, 27 of which we present in our final report. Obviously, we get rid of the issues with measurements and sometimes logistical issues in these buildings. And we ended up with a pretty large range of systems. This let us hope to understand how leakage might correlate with all sorts of building and duct system characteristics. We ended up testing supply and exhaust systems between 500 and 28,000 CFM in buildings ranging from 27,000 to 900,000 square feet. The buildings were generally office space, education, classroom space, clinical space, childcare, a lot of the types of end uses you see in commercial institutional buildings. And the numbers are pretty straightforward. Here's what we found. We measured a big range in leakage fractions. Again, leakage fraction is the percentage of air that's not reaching the final destination. And those numbers are between 0 and 29%. So we found ducts that were nearly airtight with respect to the ability of our research equipment, and ducts that were incredibly leaky at 29%. Our average duct leakage was about 7%, and the median leakage was 5%. So in other words, we have a lot of systems that leak a small amount and a few systems that leak a big amount. We also found that systems with prior sealing or tight construction were generally very tight. They had leakage rates less than 2%, and they helped to bring down this number. The key takeaways from our experience measuring duct leakage in all these systems is that sheet metal ductwork in Minnesota is pretty tight, tighter than we expected. Based on the work in California, we were kind of looking for about 15% average duct leakage, and we found less than half that, about 7%. The second thing we learned is that apparently tight duct systems are tight. This means if it looks sealed and the sealing is holding up, it's probably going to be pretty tight. And then there are certain sheet metal types of construction like spiral, welded, flange and gasketed ductwork that generally are tighter than regular sheet metal construction. We learned a lot of practical things in investigating duct leakage in these buildings. One thing that surprised us was that owner and operator impressions of duct leakage don't necessarily predict leakage. Like most people, it's very easy to notice the big leaks. So when you're an operator walking by a particular duct section and you notice leaks, it's usually because of a leaky access panel or perhaps an unplugged tab port. But again, unless you have access panels every 10 feet and thousands of open tab ports, those leaks are unlikely driving the overall leakage of the system. And unfortunately, one of the real things that we found was that there's not a big correlation between system characteristics and leakage fraction. Essentially, at the end of the day, it means that duct leakage comes from a variety of reasons, but it comes down to the way a specific system was built by a specific crew at a specific time. In fact, even in the same building with systems built ostensibly by the same crews around the same time, we find leakage fractions varying by a factor of 2. And the last wonderful thing that we learned is that measuring leakage is time consuming. The actual static pressure test only takes a few minutes, but shutting down an air handler, blocking off inlets and outlets, and then doing the reverse of that to get the system online at the end takes a long time. It's at least a several-hour process kind of per system. So that's, I guess, some sobering results. But I guess I want to reiterate that there were a lot of buildings that leaked, and we still want to know if retrofit duct sealing can work on those buildings, and we also generally want to know if how retrofit duct sealing works in a variety of scenarios. And so we embarked on this plan to seal as many of these ducts as we could in our with our research budget. And we plowed forward. And it turns out that there's a lot of ways that we could go about retrofit sealing ductwork. We have conventional methods, which are in line with how ducts have been traditionally been sealed for long times. These include applied spray sealants, painted on or sprayed mastics, and then tapes on seams. They've also have a little robot that you can put through ducts that will traverse a horizontal section and spray sealant from the inside. And then we have this new process that was very convenient for our project and for retrofit duct sealing opportunities based on an aerosol sealant that's delivered from the inside. So we hired several contractors to do this work for us. We hired one contractor to do these conventional sealing methods, and then we later hired Aeroseal. But I want to show some of the retrofit duct sealing we performed doing what we call the conventional measures. On the left, we have a worker who has got a little spray mastic wand that he is up in the drop ceiling waving around the transverse seams and longitudinal joints to seal them from the outside. In the middle, we have all the ceiling tiles have been taken out along the bottom of a supply duct in preparation of laying a long seam of butyl tape to seal up the longitudinal seam. And on the right, this is the little robot that I spoke about. It has a kind of a spray wand that rotates as the robot drives through the ductwork, and it lines the inside of the duct with sealant and seals the joints and seams. Then we've got this other method for retrofit duct sealing, which is based on a whole other premise. And actually, it's a lot like static pressure testing. This is an aerosol-based process made by the Aeroseal company that they have patented and they license out to individual contractors. But like a static pressure test, this sealing technology requires that you turn off an air handler, block off a section of the duct system. That includes the inlets and the outlets. And then you use their fan box to pressurize this portion of ductwork. The difference is that in addition to this fan box, there's also this injection system downstream. And that system injects this aerosolized sealant into the fan flow. So now the fan is pressurizing the ductwork with this flow that's laden with the aerosol sealant. And as air escapes the leaks in the ductwork, that sealant deposits on the leaks and builds up on itself and slowly slowly seals them over time. So pressure builds up, and one of the nice things is you essentially watch the sealing in real time. There's two extremely important aspects to this Aeroseal process. First, it requires a very minimal duct access. You just essentially need an access panel or somewhere you can inject this fan flow with sealant. And secondly, it has this calibrated fan in its fan box. So this means that while you do the sealing and before and after you do the sealing, you can actually include static pressure tests. So this is extremely important because the system can essentially measure how well it did. So what does this look like in practice? Oh, jumping ahead. This is what an Aeroseal system looks like deployed. I mentioned we kind of seal upstream and downstream. On the top left, we're sealing the final diffusers. On the bottom left, we're sealing at the reheat coil on a VAV box. And then on the right, we have our Aeroseal system hooked up to an access panel, and it is about ready to deliver sealant and flow and seal that ductwork. This is what sealing looks like using conventional methods. On the left, we have externally sprayed on mastic, totally encapsulating a transverse joint. That is a good seal. On the right, we have the results of the robot that traversed this duct and sealed the joints and seams and the branch takeoff all along this ductwork. In both of these cases, we have excellent seals. We may quibble about the efficiency of using this much sealant, but at the end of the day, this ductwork is very tight. Aerosol sealant, using the Aeroseal method, is a little bit trickier to see. We find that you don't really find it anywhere because it tends to deposit only on the leaks. And most of the leaks in these duct systems are actually invisible. They're buried in the twists and bends of this sheet metal. So I have a few images of larger leaks where we can see the aeroseal. On the left, we have a transition piece where a sheet metal worker was a little bit aggressive, and this resulted in like a 3/8 inch gap right at the slip and drive joint. And at the end of the aeroseal process, we seal that this 3/8 inch hole was essentially filled with this Aeroseal product, and it is now a tight seal. These kinds of opportunities to find these gaps were not very frequent, so we started drilling holes in our ductwork to see how well the Aeroseal product worked. We like to drill 1/4 inch holes because it's really easy to see them from the ground. You'd have to crawl up there and look at them. And this example on the right is a 1/4 inch hole that we drew that was then filled during the sealing process. And here's another result. This one is kind of goofy. It might be a little bit hard to see, but this is a branch takeoff off the top of a supply plenum, and there's actually a huge gap. Find my cursor. Huge gap running horizontally between the takeoff and the supply plenum. It's about a 1/4 inch thick, and it runs at least this entire section, but probably all around the perimeter of this ductwork. And this picture was actually taken halfway through the sealing process. So we can see on the left, the accumulation of that white sealant has filled some of the gap, and on the right, it's still actively sealing that, that gap. And then you can also see this entire seam is shrouded in this external insulation. So this tends to be pretty common. The ducts are sealed, encapsulated by external insulation, and you actually don't see these gaps. In this case, we cut this away, and this seam used to represent about an 8 square inch hole in the ductwork that's now been sealed in this process. So these are some of the results of what duct sealing looks like in practice. And then these are the numbers. I guess in all cases, retrofit duct sealing is highly effective. The conventional methods and the Aeroseal numbers and the Aeroseal methods. We sealed between 51 and 98% of duct leakage on the systems in this project. The 51 to 70% sealing jobs tended to be on really tight systems where it obviously gets a little bit trickier to seal down to near zero leakage. But typically in all these systems, we sealed the systems to less than 1% duct leakage. Our average sealing fraction was 81%, and our median sealing fraction was 86%. And we definitely saw that these numbers were going up in time as we work with our contractor who was new to this process, and they developed expertise here on this sealing work. So to reiterate, retrofit duct sealing is highly effective with all types of measures, both conventional methods and Aeroseal methods. However, except for a few systems, we were essentially prevented from pursuing conventional methods for duct sealing. This was mainly due to external insulation and restricted duct access. Over a majority of our systems were insulated from the outside, and they drastically limited the options. So we were kind of left with a choice to pursue aerosealing exclusively and or specifically seek out systems that could be retrofitted with conventional methods, and we pursued the latter. It was a lot easier to aeroseal these systems. Well, I guess I should say that we observed almost no constraints with the Aeroseal process. It worked on systems with external insulation, internal lining, restricted access, dirty ductwork. There was one notable restriction, and that's that Aeroseal doesn't seal very large gaps. I think they say in their product literature that it's over 5/8 of an inch gap size. And I think it could actually seal those gaps. It's just that the time for sealing them increases exponentially. So those kinds of leaks, which we have previously said are quite rare in the grand scheme of things, probably are better off being sealed manually. The other thing we learned is that whether we're using conventional methods or the Aeroseal method, the labor to prepare ductworks is really the driver of the costs. Blocking ducts for pressurization and sealant delivery is time consuming. There's just no way to get around it. I guess I mentioned earlier that static pressure testing, you have to do these things too, and that's why that is expensive. And when we compare static pressure testing with Aeroseal sealing, we find that there's actually little difference in the amount of time, and then consequently not that much difference in the cost. And then on top of that, Aeroseal incorporates the testing, and so it has this built-in method for verifying seal leakage, which is a major advantage. So now let's get into things that I know that everybody cares more about. What do typical savings look like from retrofit duct sealing? Here are profiles of energy savings that we've got from what I would call a very typical or average supply duct that is traversing a sealing return plenum. This particular system is leaking about 7%. After sealing, it leaks less than 1%. A note on that is we have a very hard time distinguishing between 0 and 1% leakage. It pretty much pushes the limits of our research, so we say 1% conservatively on final leakage. Anyway, we have 4 contributions to energy savings here on this sealed duct. The majority of the saved energy is from the heating side. So by preventing somewhere around 3 to 4% of the energy from the heating coil from leaving the building, we save 64% of our total energy savings in gas. The second biggest savings is from fan energy. We go from 7% to 1% duct leakage, and we save somewhere around 12 or 13% of our fan energy. We have a few more minor components of savings. There's cooling energy, which we're not a cooling dominated climate, so we would naturally expect that to be smaller. And then there's fan heat, which is a little bit complicated to deal with, and we essentially ignore it because it's usually less than 1 or 2%. So energy savings are predominantly gas, and then there are also significant electric savings. However, if we look at cost savings, the picture changes a bit, and this is solely due to the difference in cost of gas and electricity, but we find that when we add up fan energy and cooling energy, the cost savings on that is about 70% of our total. So 70% of our cost savings are coming from electric, and then the remainder are due to that, the gas energy we use for the heating, which is about 30%. So we've done this work to measure and describe what duct leakage looks like in terms of percentage in Minnesota buildings. We've shown, or I hope I've convinced you that we've shown that retrofit duct sealing does work really well. There's a really important piece though left, which is for us to identify cost-effective sealing opportunities. And this is what I'll talk about next. And it resulted, it was a kind of a major change in the project, because initially we wanted to understand duct leakage measurements and retrofit sealing. We didn't pay mind really to how cost-effective it was until we got to this point in the project. So we have this fundamental problem. Retrofit duct sealing works really, really well, but leakage is not known beforehand, and testing is expensive. So what do we do with that? Well, we proposed that we would study everything that we did and develop some screening criteria we could use to kind of find the good opportunities and separate them from the cost and effective opportunities. So we reviewed about 63 systems, identified all the characteristics we recorded about them, and came up with some criteria that we hope we could use to rule out the bad systems and find the good ones. And we ended up with 4 criteria. We landed on system type, operating pressure, flow rate, and apparent tightness. System types, I've talked about this already, but we look for exhaust systems traversing conditioned space, supply ducts located in return sealing plenums, supply ducts with ducted returns. I mentioned earlier that pressure drives leakage, so we want higher pressure systems in order to find higher leakage. We say at a minimum of 5 inches water column, we'd prefer over 1 inch of water column. And then again, leakage requires flow rate. We need to set a minimum floor for the size of these systems so that it justifies bringing out a crew and sealing them. So we say we like systems greater than 4,000 CFM, we prefer 10,000 CFM. And again, apparent tightness. If a duct looks sealed, it probably is. This isn't to say the opposite, that if a duct looks leaky, it is leaky, but we can rule out systems that look tight. So based on this criteria, we kind of restructured the project to go out and test whether we could actually find cost-effective systems based on simple screening. We asked our contractors to go out there and go about their normal business, but bring back to us the systems that were meeting our criteria. And we said the first 5 systems you bring back to us that meet these criteria, we are going to seal. We're going to use the Aeroseal equipment to test how well we predicted leakage and whether we identified cost-effective opportunities. We found and sealed 5 systems. We had 5 supply systems. 4 of them had sealing return plenums. 1 was fully ducted. They ranged about an order of magnitude in size, from about 4,000 our minimum up to 40,000 CFM, and they had operating pressures between about 1/2 inch and 1 inch of water. These systems were significantly leakier than our initial set, and maybe this shouldn't be surprising. I've mentioned a few times now that leakage depends on flow and pressure, and once we start filtering through these things, we find much better results. So these systems leaked on average of 23%, ranging 11 to 66%. So here are those results. We sealed between 800 and 18,000 CFM on these systems, and we saved between about $350 and $11,000 a year on these systems. Payback averaged about 7 years and varied between 2.5 years and 17 years. So these were really successful results. In most of these cases, there was direct and immediate feedback from the staff saying that they didn't really know that there was leakage, but they noticed operational changes in their systems. So what do we do with this? We've identified that simple screening process can go a long way to identify cost-effective opportunities, but what are we going to do to make this happen? Recommendations for moving forward. Basically, we need to immediately incorporate at least duct sealing screening into existing programs. It's very easy to do, and it should, as of today, be considered in commercial auditing, recommissioning, and turnkey savings programs. Duct sealing also makes sense in as a bundled measure or service, and this includes for energy efficiency and non-energy efficiency reasons. It goes nicely with duct cleaning, any kind of rebalancing work, motor, VFD, or air handler upgrades, and any kind of renovations. As a side note, a lot of the systems we visited in this project were changed significantly over their lifetime, and those would have been perfect opportunities to update the duct system and reduce leakage. And it could also be added with other commercial program savings measures. Part of that might be due to the risk. We should acknowledge there is some risk because we don't know leakage ahead of time, and we can alleviate that through bundling. Again, I've mentioned this already, but the integrated M&V on this Aeroseal in particular is an extreme advantage, and it makes it easy to do performance-based rebates. I would say that I didn't touch on it here, but we put the Aeroseal rig through a calibrated fan flow facility, and we found that it essentially matches our research grade equipment within 2-3% on most of the important flow regimes. And I will acknowledge that our project is limited here in the scope. We were only in 30 buildings or so, but what we need to start doing is proliferating these screening efforts and sealing results so that we can kind of build on a public knowledge base so that we can continuously improve our screening criteria and maybe streamline and even make this process cheaper. But there's a lot of steps to get there still. We need to do some outreach. Commercial retrofit duct sealing still remains under-recognized in the commercial space, but it is an energy issue. I hope, if anything, I've convinced you of that. And there still remains some skepticism on the efficacy of duct sealing, and I hope I've shown you today that if nothing else, the retrofit duct sealing does work. We need to educate the vendors about duct sealing, about the energy issues, but we also need to educate them about the risks. We need to get people comfortable with the idea that duct leakage will usually not be known beforehand. There's also another part of this, which is that savings from retrofit duct sealing are reduced if the existing system is not meeting its goals. If it's not ventilating, heating, or cooling properly, due to duct leakage, and we fix that duct leakage, that will reduce our energy claims. That said, if a building is failing to meet its basic services, there's obviously non-energy reasons for sealing our ducts. It's important to emphasize that despite these risks, we can significantly reduce them even with very basic screening efforts. And then again, I've shown you just 4 basic criteria. These are things that most staff can get a handle on. We can start screening with building staff, contractors, tab firms, and duct cleaning and abatement firms right now, as long as they kind of understand the background and what we're trying to do here. So, in the end, we measured leakage. It was a lot lower than we expected, but there is still an immense opportunity. I mean, we're talking about even looking at the systems, the 15% of systems with high leakage, 460 gigawatt hours a year electric, 2,900 million cubic feet of gas savings opportunities a year. A lot of energy moves through commercial and institutional distribution systems. Even fixing a small amount of that is going to have massive savings. We estimate that about 15% of C&I buildings will yield cost-effective opportunities. approximately a 7-year payback. This product has a long lifetime, I would say equivalent to the duct system life. Duct sealing works. Our retrofit duct sealing worked in all cases, and the existing sealed ducts that we found were very tight. The main advantage of Aeroseal is that it greatly expands the opportunities. It really makes this retrofit market possible. Again, the energy penalties are mainly from heating in most common systems, but the cost penalties are mainly from fan power and cooling through the electrical side. Cost-effective sealing depends on system attributes. We found that if we select systems based on type, size, operating pressure, and existing tightness, that we can successfully find good cost savings opportunities. This simple screening approach can be applied widely starting now. The Aeroseal process is built-in M&V for reliable performance for base rebates. I will say here that 3 of our 5 pilot sites ended up independently pursuing custom rebates with their utilities, and that, to my knowledge, was a fairly painless process for all of them. Duct leakage measurements should be immediately incorporated into all existing commercial programs, and screening efforts should be implemented starting right now after this talk. That is about all I have to say today. Thank you for your time and listening with me. Before I end, I do want to acknowledge that my colleagues Ben Shainbauer and Dave Bohack put in equal time on this project. And I'd also like to thank Mary Sue at Department of Commerce. She helped us restructure this project over at the end to incorporate this pilot, which I think greatly expanded the utility and showed the promise of retrofit duct sealing. I'm happy to take questions if we have that time. I'll also be available offline to talk about this talk, our report, and or whatever you have in mind.
Wonderful, Josh. In the world of technical webinars, I feel invigorated. So this is, I hope you've found this very informative, and I'm just going to quickly move down here to, I think we have slides that are duplicating up on themselves, to a question and answer slide. And as I did mention before, we are going to be having these slides available online yet today, and then the recording shortly thereafter. But maybe we'll just start off. We have a few questions that have come in over the time of the webinar. Early on, Josh, you referred to a code and code where there's going to be increasing amounts of testing on ducts or new requirements on sealing for, in this case, high pressure duct systems, and some recently for low pressure duct systems. Could you just say a little bit about what code that you're referring to?
Sure. I think the energy code that came out in 2015 for commercial buildings now specifies that we should be sealing low pressure ductwork to Class A standards. And this, you can interpret it, I still think, in many ways, but it basically means we need to be sealing all the transverse joints and longitudinal seams. And this comes from, I think the language is much of the same, but it's in both IECC 2012 and ASHRAE 90.1.
Great, thank you. It's a very good question. There's overlap, of course, between the mechanical code and the energy code. Another question is, have you had experience, or do you know if the sealing techniques that you're talking about, and I believe this question came in when you were specifically talking about the aerosol sealing method, but does this work for underground ducts that might have water penetration or exposure to water?
Wow, that's a really great question. I would probably have to defer that to Aeroseal staff. We did not really pursue underground ductwork. Part of our initial characterization work led us to focus exclusively on sheet metal ductwork with a little bit of gypsum board and fiberglass ductwork. And I can say with respect to fiberglass and sheet metal, it works great. I don't know about the water tightness. With respect to gypsum board ductwork, like, for example, ventilation in multifamily buildings, that is a whole other can of worms that I will say for a later date.
Thank you. And certainly if you do have interest to learn more about any of the technologies, the sealing technologies that we discussed, you could write to Josh after this, and we can put you in further contact with any of those companies, as they do have, of course, specific product information. Another question about the aerosol sealing method. Did you see any deposits of the sealant on fire dampers or other linkages, etc., where there might have been causing any concern? I think maybe sort of multiple types of fire concern for others.
Nope, we haven't seen any problems with aeroseal depositing in any, I guess, undesirable locations. We have seen that some facilities are very sensitive about this. In that case, the sealing crews will specifically block around those areas. But in cases where they haven't been that cautious, we also haven't seen any problems, specifically with fire dampers and or shafts. And another thing they will typically block, though, is if there are sensors in there they don't want to gum up, static pressure sensors or temperature humidity sensors.
Great. Another question is, just in general, you talked a fair amount about characterization or the strain, the difficulty of characterizing which ducts should be sealed. But if a duct is generally quite old, should that be an indicator that it's maybe due for resealing?
That's a great question. Actually, we found that in most of the older systems, and we were in some that were dating back to the 60s and 70s, that the sealing generally held up quite well. I can recall one building in particular that was not the case, and that for whatever reasons a lot of the sealing had become embrittled and fallen off. However, I will say that in that case we used that as a justification to seal the system, and it didn't get that much tighter. What that meant to me is that the sealing that was falling off externally wasn't actually the sealing that was blocking the ducts, and the stuff that was stuck into the metal bends and twists was robust over time.
A question that I will put to you, Josh, even though it might be a good follow-up question for Aeroseal, but what is the life expectancy of the Aeroseal material?
That's a good question. I know that it hasn't been around that long, so it's certainly not been field tested for 30 years, but there has been work, and I've read a report, I think it's out of Lawrence Berkeley, where they did accelerated testing on simulated seals, where they did a lot of pressure and temperature cycling, and they compared that against all manner of other duct sealing products, and virtually everything failed except for the aerosol sealant. And I think that speaks volumes to how long it's going to last in the field. I can say that it's quite different than a lot of the other materials we find. It's somewhat elastic, so that it's probably not going to have the embrittlement problems that traditional mastics have. So while it's only been out there a short amount of time, I think that accelerated testing means good things. I just see that Vicki at Aeroseal said that there is a 10-year guarantee on the sealant, and I have no problem believing it will last that long, if not significantly longer. I would typically think of it as the lifetime of the duct system.
Great. I think we just have time for one or two more questions. But you did mention that there are 3 utilities in the state of Minnesota that have done some sort of sealing project in general, probably in a custom manner. But do you know of other utilities across the country? Is this a trend that you've heard about?
No. I don't know much about what's happening. I know in speaking with Aeroseal over the past few years that there have been lots of custom rebates issued throughout the country, but I don't know if that's evolved into any kind of specific programming.
Great. And what you mentioned before about our climate being, heavy in heating and some of the additional energy savings that can come from that, we might be a prime market for that. So I think our last question was actually just kind of a follow-up on a previous question, which was when asking about the depositing of sealant on kind of fire dampers and things like that, where you might not want there to be sealing completed. Did you have any troubles with that or examples of that happening with the other sealings methods that you use, like with a robot sealing?
No, we didn't find any issues with the traditional sealing techniques either. I will say that we only ultimately sealed a few systems with the conventional techniques that we were able to. It was very hard to find systems that that worked that way. I think even the sealing contractor we worked with found that they had maybe overestimated their abilities to work in and around occupied spaces. And so unfortunately, our tests ended pretty quickly.
Great. I'm actually going to ask one more quick question because I think this is a really good one. As far as a supply of contractors that are able to do the varieties of ceilings that you've talked about today, can you maybe just say a little bit about that in the Minnesota market to the extent that you know?
Sure. Well, when we started this project back in early 2013, there was no Aeroseal contractors in Minnesota, and our plan was to actually work with Aeroseal directly, based in Ohio, I think. But thankfully, once the project was really underway, about a year later, there was a contractor that became licensed in the state, and that vastly simplified the work on our project. We ended up working with them quite closely over a few years, and then I believe they had maybe a unique or exclusive license for a while, but over the course of our pilot, at least one other contractor has become licensed, and maybe more beyond that. And we didn't get a chance to work with the second contractor directly, other than that they were out there trying to identify systems for our pilot. And I think that the other sealing techniques are really available to anyone. I think that there may be some licensing involved in the robot, but I couldn't speak directly to that.
Great. Thank you very much, Josh. I think this has been a great morning of information. And I'm going to turn it back over to Mary Sue at the Department of Commerce again, just to kind of help us close out this morning's webinar.
Well, thanks for attending this card webinar. I hope you found it as useful as I did the project. And you can find this recorded webinar and other recorded webinars, as well as card reports, by going to the card webpage on Commerce's website, which is displayed here. And to find reports, you can use the card search tool, quick links on the right there, and search for a specific project by technology, market sector, or grantee. To find recorded webinars, you can use the card webinars and video quick link, which will take you to a listing of all card related webinars and videos. And this particular report from this particular project is posted now. It's posted as of Monday, and I sent the link to Megan. So she should be able to include that in the communication about the webinar afterwards. But before I leave, I wanted to mention some upcoming webinars that are coming up. On May 24th, Franklin Energy will be conducting a webinar on the T12 lighting saturation study. On June 14th, CE will conduct a webinar on reducing envelope leakage in multifamily buildings using the aerosol sealant. On July 12th, not the 19th, but the 12th, Center for Energy and the Wisconsin Energy Conservation Corporation will conduct a webinar on the small embedded data center pilot program. And then on June 22nd, CE will conduct a webinar on improving the effectiveness of commercial energy recovery ventilation systems, which I think will again be done by Josh. So we look forward to having you attend any of these webinars. If you need information on how to sign up for any of these or have any questions or feedback for the CARD program, please feel free to contact me.
Thank you very much, Mary Sue. And with that, we'll conclude today's webinar, and I just want to point out that if you are interested in finding the recording of this webinar, you'll find it under resources on our homepage. You can go down to reports and materials, and you can find where we archive our webinars there. And then if you are interested in hearing about upcoming webinars and events, particular to our research, you can find our newsletter link at the bottom of any web page and simply sign up there. Thank you very much and have a great rest of your day.